Okay, hey everyone, welcome to week 7 of the Python DeCal. So first for some announcements. Homework 5 will be due on Wednesday at the usual time. And we just released solutions and grades for homeworks 1, 2, and 3. So definitely check those out on B courses. Let us know if you have any questions about anything. And also make sure to come to office hours for any homework help, or just if you're having questions about the course material in general. You could even just come and sit on the side, and then when you are stuck, just ask us for help. So you don't necessarily need to have like a list of questions when you do show up to office hours. So we definitely want to encourage everyone to try to come to those more. And also, more importantly, it's time to start thinking about final projects. So it's kind of like mid-semester still, but we're gonna release a survey on B courses. It'll just be a short Google form, and you'll just fill out some basic info about like what kind of final projects you're interested in, and then we'll form you into groups of 4 so that you can actually start working on them. So for some more details about the final project, this is mandatory to pass the class, so everyone needs to submit something. As I said before, the final project will be groups of 4, so you can either request people that you may know in the class, or otherwise we'll just put you randomly into a group. And so we'll be releasing the survey later today, so look out for that on B courses. It'll be due this Wednesday. And it's really important that you fill it out on time so that we have time to make your groups as well. And then some dates. So the project proposal will be due in about 2 or 3 weeks. And then the final project presentation will be due basically the last week of classes before dead week. Yes, question?
Are there like examples of final projects?
Yeah, here's the slide. So here are some ideas. So we have like analyzing some astronomical objects. So like we kind of talked about making light curves for supernova before. You can explore that more. So if you're taking some astronomy classes, you also know about HR diagrams. You can do something more on the physics side. So like the trajectory of a pendulum or even a double pendulum. Then you also have simulating transit methods. And then if you don't really want to do something related to astronomy or physics, one group last semester did a Sudoku solver, which was really cool. And another group made this animation of these Mandelbrot fractals. So there's a lot of different ways you can go about this. And also check out the website. We have a lot more examples on here. So you can see like every semester previously, all the final projects are here. So if we go to fall 2021, you can just click on any of these presentations and take a look at what people have done in the past. And here are some pictures of some cool stuff you can do. So here's like a transit method like simulation, as well as some like galaxy simulations. So really, there's not any criteria or bounds you need to fulfill, just that you code something cool in Python. Okay, does anyone else have any other questions about the final project so far? Okay, just make sure to do the survey on B courses by Wednesday. Okay, so let's do a quick recap of last week's lecture. So I think it was James was talking about, or James and Raphael were talking about using the SciPy curve fit and mp.polyfit so we can start fitting our data to lines. So like we've probably done in class before, like y equals mx plus b, and how to fit this line to data. And so we saw that you can use curve fit and mp polyfit to do this in code, and it's a lot more efficient and accurate. So does anybody remember the difference between curve fit and mp.polyfit?
I don't quite remember, but taking a guess, was curve fit you select the function yourself, whereas polyfit it fits the closest function you can?
Yeah, exactly. So for curve fit, you have to define the function you want curve fit to fit to. So you have to write out, like if you want to do a line, you'd have to do like def f and like return mx plus b. Whereas for polyfit, you can just specify how many degrees you want to fit the polynomial to, and it'll fit a polynomial. So curve fit in general is a lot more general, and you don't necessarily have to only do polynomial functions. Okay, and does anyone remember what curve fit was minimizing? So how does curve fit return the one optimal solution? Why aren't the other solutions as good? Like, what is the thing that it's minimizing? Yes. Yes, you. Yeah, so I think we talked about chi-squared, but I think curve fit in general is minimizing the least squares thing, which is a bit confusing. You'll learn more about it in stats. But I do think curve fit, you can also specify what error function you want it to minimize on, but by default, it's the least squares. Okay, so for today's lecture, we'll be going over differentiation and integration. So we're kind of continuing on from last lecture's idea of numerically doing some data analysis. And so today we'll be talking about derivatives and integrals. So as a quick review on derivatives, derivatives are basically they show the rate of change of a function at a given point. Or you can also say it as like the instantaneous tangent or slope of the function. So here we have this blue curve is cosine of x, and the derivative would just be negative sine of x. And so you can see both of them plotted here as the original function and its derivative. So in general, derivatives are going to be really important for data analysis, and it'd be really useful if we could also do this using Python. So like before, we're basically just going to use a function from SciPy. So you first will import it. So from scipy.misc, import derivative. And then you can just use this derivative function, which will do everything for you, like behind the hood, kind of. So you don't have to worry about implementing it, which is really convenient. So like curve fit, you also need to pass in the function that you want to integrate. You also need to pass in the point where you want to evaluate the derivative. So if you want to take the derivative of a whole graph, like before the derivative of cosine of x, you would first pass in this function, cosine of x, and then you would pass in the x values you want to evaluate your derivative at. And it's pretty cool that this can either be one value or it can be an array of a bunch of values. So we could have passed in our cosine function as well as the entire x range from like negative 2 pi to 2 pi, and then it would return the derivative over all of the values. We also have to include an argument for spacing and also order of differentiation. So if you want to do like the first derivative versus the second or third derivative. So last time we also talked about defining a function to pass into your SciPy function. And so we've already saw in class that this first way up here is the way we've been doing to define a function. So you have your def statement, the function name, arguments, a colon, as well as some sort of return statement. And so a lot of times if we want to just do a really quick function, like we all know, like y equals mx plus b, and that's really simple. We don't want to have to write out this whole thing every time. You could instead pass in a function into an argument in like one line basically, because you don't really need to save it otherwise. And so here, the syntax, you need to be careful to use this lambda. This is one of those keywords in Python. So if Python sees the word lambda, it knows that you're defining a short function. This x here is the same as like what this x in the argument of function does. And then after the colon is just anything you want to return. So you can see here that this top way and bottom way are the same. but this is just a little bit quicker for if you want to just pass in your function once and not use it again. Okay, and now I'll pass it over to Maham to talk about integration.
So after you learn differentiation, the next thing you learn is integration. And what integration, there's like several ways you can integrate something. One of like the basic ways that we start in our calculus classes are Riemann sum, where we just like kind of draw like rectangles or trapezoids under our curves, and we try to find the area by adding up all those curves. And then there's also like Simpson's rule, which is a pretty complicated formula. So over there, you'll see like a diagram of how we just draw rectangles underneath a curve and find the area. And that's Simpson's like really complicated formula. And then Gaussian quadrature is another way of doing it. And according to James, it's the best way of doing it.
That's true.
And so when we do it in Python, it's obviously an important skill. And when we do it in Python, we would want to, instead of importing just something specific from SciPy, we'd want to integrate like all of the integration functions, because there's like a lot of ways you can integrate things. And here are 2 ways you can do it. And here's a cool meme that you can think about when you're integrating an indefinite integral. And here is like the key functions, all the functions that SciPy integrate offers, and then the key ones are the ones with stars on them. And you'll see quad, double quad, and triple quad, and then traps and simps, which we'll be doing quad, traps, and simps in our demo today. And yeah, so here's an example of how you would do an integral. So like you can, and then so here you have your function, and then your lower bound and your upper bound. It's pretty basic, but when you do print it, it'll give you 2 values in parentheses, and that's just like returning a list. And the first value will be your actual integral, and the second value will be your error bound, so like plus or minus however much the error bound is. And if you just want to get specific, if you just want the error bound, or if you just want your actual value, you just got to do integral 0 or integral 1, just like how you would like index items in a list. And here's a way to do double integrals, which is like when you're doing integration of multiple variables, it's just adding more arguments. And you'd also want to be a little bit careful about like when you have variables in your bounds. So like the next example will show like you'd want to be careful about how you're using lambda. It's the same thing, your function, your outer integral, and then your inner integral, and make sure you're careful about how you're using your lambdas. And we'll do examples, and we'll discover like what even is lambda. So if you're a little bit confused about that, we'll cover it. And now it's time for demos. So hopefully everyone downloaded the demo that was emailed yesterday. Do you mind opening? Does anyone have like any questions over the content that was just covered? Yes. Oh yeah, sorry, I kind of ran through it. So double quad, again, is just like another integration technique. Well, not integration, it's like another way to, it's just when you're integrating multiple variables, and you start with your function, which in this case would be x times y, and then you have your outer thing, and this first argument will be your like outer integral, and it'll be 3 and then 6, which makes sense, and then your inner integral, and you can't just put x squared, and we'll talk about that when we're doing our demo, and that's why you need lambda x, which is like defining a function inside your integral. Does that make sense? Okay. All right, so here we have our import statements. Make sure you run that cell. And here's like a little debrief about what we covered in the slides about derivatives. You can kind of look at it and absorb it, but we're gonna move on to the chunk of the demo. Make sure you run your import statement. That's the import statement if you ever want to run it. And now it's gonna go ahead and take like 3 to 5 minutes finding the derivative of cosine and sine at 0 and pi over 4. And if you need help, just raise your hand or talk to each other.
Yeah, I'll put the people on Zoom into a breakout room. Give me a second. Okay. Yeah.
Right there. Okay, do I call them out of the breakout room?
Oh, yeah. Okay, while we wait for the breakout room people to come back, so the survey has just been posted to B courses. So if you have some time now, fill it out, or just make sure to do it before Wednesday.
I have no idea if they came back.
They're not back yet.
Okay. Maybe they're chilling in there.
Yeah.
All right, so now we're going to do it together. So for the first example, all you had to do was have derivative because that's how we oh. Oh, the red X, my bad. Yeah, and then all you had to do was, in the first argument, we had to have f because that's cosine. And then in the second argument, we had to have the point that we wanted to evaluate it at, which is 0. And in the third argument, we could put, like, for more precision, we would want to put like 1e to the negative, which is just saying 10 to the power of negative 6. And then when we run it, I didn't run the first. My bad.
Try running this again now. I think it should be okay.
Okay. Yay. So obviously this would always be 0 whether we had that argument there or not. Well, it would matter if we were doing it. So I'm going to say this is cosine, I don't know, underscore cosine 0. Now let's do sine of 0. And then when we take the derivative of that, all we would have to do is call g 0, and we can again have our dx defined as 10 to the power of negative 6, and then we can print sine 0, and then it would be like super specific. If we didn't have this dx at the end, it would be another kind of value. But for if you want a more accurate value, that's what the dx does. And we can also do for sine pi over 4, sine pi 4. And that's what we get for that value. And then what we want to check is if sine pi 4 and cosine pi 4 will be the same. Ta-da. Why is it negative? Yeah, that's why. Yep, so ta-da, that's how that works. Does anyone have any questions? All right. How many of you guys were able to do the next part? Yeah, oh yes, what's your question?
So can we also replace like after like derivative and the parentheses, could we instead of saying f, could we type out like np cosine?
Yes, that would also work. So if you just want to say np dot cosine, I messed it up. Okay. It'll also work. Any other questions? All right. Who was able to not do the second part? Okay, not do the second part, as in like you were able to attempt it. Who was not able to even like look at the second part? Okay, let's do 2 more minutes of just looking at the second part. Or should I just do the second? Okay, 2 more minutes of looking at the second part. The point of the second part is that you'd get some kind of error, so don't worry about getting the error. We're gonna figure it out together.
Okay, so we'll just wait. We don't need
Do
to
you
break.
want not breakout room?
Are you just doing like 2 minutes or like?
Okay, yeah.
Okay, cool.
Oh, yeah.
All right, so now we're going to figure out what the error is. So the point of this part of the demo is like, okay, let's plot the derivative. And I guess the first instinct would be like, okay, let's first make a y prime and say derivative. And we want to take the derivative of f at x. And then the next step would be to take y prime and plot it. But as you'll notice, it's an error because what's happening is that we're taking like this whole array of x's and we're just like dumping it into the derivative function. So the solution to this is like to define f as a function of x. And so all we got to do is turn f into a function. And to do that, we're going to use a special function, lambda. And I'm going to define my lambda as a, and I'm going to go to all my variables and change from x to a, as like that. And then I'm going to say, okay, my y is equal to f of a, f of x, my bad. So it's going to literally, it's taking, f is my name of my function, and it's taking x as the argument, and it's going to take all the values of x from here, and it's going to put it into this statement. Does that make sense? All right. And so now I'm going to take the derivative of y, comma, x, and now, hopefully when I plot it, nothing bad will happen. And I'm adding plt.legend so we can see it'll label the different axes. Just make sure nothing else got missed. Okay. Oh, okay, I was supposed to change this. Oh, my bad. My bad. Sorry. Yeah, this can. That's why.
Oh.
Yeah, this can be
Okay,
f
maybe
or
you can-
y. We're gonna.
F of X here.
Oh yeah, it's over here.
Yeah.
Oh, sorry. Sorry, guys. But yeah, so when you're taking the derivative, it's gonna be f, comma x. I think I'm. Okay. Hopefully, when this runs. Yay! Now we have a pretty graph, and it shows you the blue line is y, and then the yellow line is the derivative of y. Does that make sense? Yeah, sorry.
Yeah, I think the bug earlier was just that we were passing in y, which with like an array of values, but we need to pass in the function. So that's just that. Yeah, all good now.
Yes?
Why do you need the y equals f of x if you could put y and just y as f2 for the simple class?
I guess it doesn't need to be there. I guess like you can easily do f over here. Oh, okay. So the reason I needed to do that was because if I put f here, it's no longer, this f is no longer in terms of x, so it's going to freak it out. I guess I can show you and run it. It's not gonna be able to plot y. So this line was essentially a solution, so I can graph the original y. And then this is y prime. Yeah, sorry that was a little bit lost in translation.
Yeah, if you don't want it to find your y, you could have done like plt.plot x comma f of x, like f parentheses x. Yeah, because f is like a function object, but f parentheses x is the return of that function.
All right, is everyone ready to move on? Okay. Okay, so for the next part, we're introducing integration once again, and here are some of the neat things that we can use. There's also a triple quad method. We're going to be doing quad method, trapezoid method, and Simpson method. So obviously don't forget to run your import statement, and then for the final exercise, just go ahead and take this velocity function and find the derivative. And I'm sorry, not the derivative, the displacement. And to find the displacement using a velocity function, you got to integrate it. So you integrate it using the quad, trapezoid, and Simpson method. And go ahead and spend 5 minutes on that. And you can work with the people around you, or you can raise your hand. And if you have extra time, you can also mess around with the extra arguments.
And we're gonna make a breakout room for the people on Zoom. Where'd it go? Oh, breakout rooms. Okay, let me take a picture of this. Oh, yeah, we might want to make this smaller then, because it was doing weird things before.
Oh, okay.
Oh, I guess I have it here. Okay, never mind, never mind. It's probably fine.
Hopefully.
Okay, no one can fact check you.
I mean, I went to an integral calculator,
Okay, cool, cool. Okay.
but these were really off because it's
Uh,
like very different than that.
Yeah, it's fine. Yeah.
I guess it's like showing which method is the most precise.
Yeah, you can also just say like, yeah, to make these more precise, we could change these.
Okay,
You know?
yeah. I also forgot to do the different weight things, but I'll do it at the end. Yeah, so it's similar to like the last question. So how do you, what you do is that you define your function or and then set it. What's happening is do it like this. Yeah, so what's happening is that
Because this one defines it as a function, so why do I have to like define it as a function and define it as another function of a different variable? Like, I don't understand.
and then for this one, you're searching up for a specific function, it'll show like the data type that you're good. Can you spell it? And it'll show you over here, it wants an array like input, so like whatever you put in, so like for your y, it's the one that's the
So it doesn't want to function.
it doesn't exactly, yeah.
Now let's try
And
to.
that's why it's really important.
Okay, yay! And so this is
If you
like
go back to the
the
when you want to test it out, you
now
know,
you can
when
try
it
using
gets
it
and see what the error is.
changing
Yeah,
what's
it's
in
just
it,
a
a
list. Yeah, so it's specifically complaining about the types of element.
Yeah, so after equals 0, it's just saying you want to integrate with group perspective. Really good to do. But yeah, so this is talking about it. Function here, we need like a mathematical function, not like a Python.
I should clarify.
Yeah, that would make a lot of sense.
All right, so I'm just gonna jump right into the solutions. So what to start with is just to have an array of like the values of whatever like what you want your range to be. So for me, I did 2,000. It can be 1,200. I just did 2,000 just to be safe. And then I'm going to set my v, and I'm going to make it a mini function. And I'm going to set it again as a different variable. And I'm going to write down the variable, write down the function I had above. And then I'm going to do again what I did in the first question and just have my velocity as a function of time. And then we're going to do my quad integral. And have my function as the first argument and my bounds for the last two arguments. And then when I print it, it'll give me a list of values. Oh, rip, my bad. Yeah, my bad. No, not another error. My bad. Yes, I did. Okay, into. Yeah. Ta-da! Another list of values with this as the actual integral and this as the error bound. And just to quickly show what the syntax would look like for the other two, is instead of using the function v, you'd want to use the function v of t, or you, as I defined it as velocity, and then have like all of the statements above, and then when you print that, it'll give you, no, not another, okay, I'm gonna do it as velocity. My bad. Yeah, I'm so sorry, guys. It's my first time up here. Yeah, and there's your value for traps. And you'll do the same thing for simp. And if you have any questions, you can stay, but class is over now. Sorry about the overtime.
There is a new resource that is going to be uploaded to the courses in like a minute